Hey everyone, it's Dr. Collins again. So back with another regression video. Today we're going to be doing something a little bit sort of between bivariate regression and multiple regression. We're going to talk a little bit today about model fit. So this often falls under the umbrella term of diagnostics, model diagnostics. So it's after you run your model, after you estimate your model, right? So in this case, it's our linear model. After we estimate that using regression, we go back and we check up on it to see how accurate it is, how good it is, how well it fits with the data. So that's something we're going to talk about today. And then we'll dive a little bit into dummy variable regression, okay, which is bivariate regression. And it sort of works as a nice segue into the next discussion that we'll have, which is multiple regression. Okay, so we're going to continue with the same example. So if you recall, I said that the #1 country for women in the lower legislative chamber is Rwanda. However, #2 is Cuba, with around 53% in their National Assembly of People's Power being women. So that's why I've got here Cuban colors, the Cuban legislature. Okay, so our agenda, we're going to assess model fit. Okay, there are really two things I want to talk about there. We're going to talk about the first one, which is known as root mean squared error, which is exactly what it sounds like. And then we'll talk about the more common and the more useful of these two, which is called R squared. Okay. And then we're going to talk about, right, in our last example, we talked about having a ratio or interval level dependent variable in our bivariate regression. This time we're going to talk about what happens if you have nominal independent variables. Okay, so we'll start by talking about dummy variables, and then we'll talk about polycotomous nominals. Polycotomous means simply that it has multiple values, not just two, right? It's not just a binary 0, 1 dummy variable. Okay, all right, so let's dive right in. So if you recall, here's our running example. So we're looking at that Women's Civil Liberties Index, which ranges from 0 to 1, and the percent women in the lower legislative chamber. We fit that model in the last video. If you haven't seen it yet, obviously go back and check that out. But otherwise, there is our model. Okay, so we see there that we've got our regression estimation right here. There's our t-value, which of course the t-value means that this coefficient 13.56x, that coefficient 13.56 is in fact statistically significant. So we can reject the null that in the population, Women's Civil Liberties Index has 0 effect. Beta in the population is 0, basically. Okay, so now that we've done that, we can take a look, and obviously we see that this line doesn't perfectly fit the data. Very rarely, in fact, never, should your regression line perfectly fit the data. All of the observations are not going to fall directly on the line. In fact, if they do, it usually means that you have some wonky data, right? Like for instance, if y is equal to 2x, right? So if you take some variable x and you double it and that becomes your y variable, then of course it's going to fit on the line perfectly, all right? But unless y is some direct transformation of x, you don't expect the data to perfectly fit on that line, all right? However, we are curious about those errors. Okay, so you recall we talked about the errors. We talked about how Ethiopia is not very close to the line. Yemen's not very close to the line. You can see that Rwanda and Cuba are not very close to the line. Each individual error, which we called U sub I, those are often called residuals. So when you hear discussion of model residuals, that's what they're talking about, right? Things that don't perfectly fit on the line. That tells us how well we've estimated Y for that given value of X. All right, so for each individual observation, we can say, all right, it's this far away from our predicted value of y. So we know Rwanda is pretty far away from the line, right? So we predict Rwanda should be around 20. It's actually over 60. So our error there is 40, okay? Similarly, we look at countries like, I don't know, the Dominican Republic. Our error there, right, if you take a look at the Dominican Republic, which is right here, that error is pretty minimal, okay? So the question is, what do we do if we're trying to assess the distance between each point in the line for the whole line? We want to assess how accurate our line is. Okay. Well, we have to assess model fit. If we want to know how well our regression line performs, that is, how accurately it represents the data, we need a goodness of fit measure. So you've heard goodness of fit. We've talked about chi-squared goodness of fit. This is different, right? This is generally a way to assess your model fit. One way is to average those errors, those individual error terms, U sub I. And this is called the root mean squared error. And it's called that because, hey, shocker, you square the error, you sum them up and divide it by n. So you take the mean of the errors, and then you take the square root. So guess what? It's the root mean squared error. So for Ethiopia, right, that's going to be a positive. You square that. For Yemen, that's going to be negative. You square that. You add everything together. You do that for every observation. You add them all up. You divide that by n, and then you take the square root. It really just works out to the average, basically, the average distance. Okay? So the way we interpret this is in terms of y, right, in the units of y. So for example, in our running example, our root mean squared error for that regression line is 11.66. Right? So if you went through and you calculated those distances, you squared them, you added them all up, divided by the total n, which is 173, took the square root, you'd get 11.66. So what does that mean? Well, we can actually interpret this pretty straightforwardly. On average, our regression line's predicted value of y is 11.66% off from the observed y, that is the percent women in the lower legislative chamber. Okay, so on average, we're about 12% off. Is this good? Is this bad? Well, obviously, it sort of depends. Given the range of y is from 0 to 63, 11%, not that bad. Okay, but this doesn't tell us a whole lot. Another option, and in fact, a much more useful option, is to look at how much of the variation in y, so how much of that variation from 0 to 63 in y is explained by accounting for x. All right? So if we look at a Venn diagram, we have our two variables, y and x. Right? Here's y, here's x. The circles represent the variation in these two variables. Right? So if y has a lot of variation, the circle's going to be big. If x has a lot of variation, the circle's going to be big. All right, but this is sort of dumbing it down, not for you. It's just sort of a simplistic way of looking at it. You're not dumb. All right, so looking at this, right, we see that A is the portion of the circle Y that does not overlap with X. C is the portion of X that does not overlap with Y. B is where they overlap. Okay? That's what we want to know, right? We want to look at what is this total, right? As a share of all the variation in y, how much of it is in this b, okay? So what this is it's actually called r squared. The r squared value of a regression model measures the proportion, so it's proportion, of the variation of y that is explained or shared with x. Put another way, it's b divided by a plus b, right? So how much of the total portion of y, how much of the total variation of y is covered by x? So b is what portion of a plus b, okay? Make sense? Moving on. Now the units of y don't actually matter in this case because it's a proportion, right? Doesn't matter what the units of y are. This is going to be the same way to interpret this across all different models. It's the same interpretation for every regression you run. All right? It's our independent variable or variables as we get to multiple regression. It's the proportion of variation in our dependent variable that is accounted for by including our independent variables. Okay? So we start by calculating the total variation of y. So that's a plus b. We want to know what the size of this circle is. All right, this is known as the total sum of squares. And it's pretty straightforward. It's just the deviation of each individual point squared summed up. All right, so overall, how much variation is there? That's the total sum of squares. All right, so you take yi, that is your observation, y at that observation. the value of y at that observation, minus the mean of y, and then you square that. And you do that for all 173 observations in our example, and you add them up. Then we calculate what's not accounted for by x. That is, we try to figure out what's in A. This is the residual sum of squares. Now that word residual, I mentioned it before. All right, the residual is just each individual error. So it's really just the squared errors. That's it, the sum of squared errors. All right, so this part here is basically the errors in our prediction. So it's the variation of y that is not accounted for in our model. It's those errors. All right, so you square them up and you sum them. Then we figure out what share of the total sum of squares, all of y, is not covered by A. So what portion of A plus B is not covered by A? So basically, what portion of A plus B is covered by B? So R squared then is just calculated as 1 minus the residual sum of squares divided by the total sum of squares. So residual sum of squares is A. All right, so proportions, right, they sum to 1, right, 100%. So a proportion maxes out at 1. So what you're doing is you're saying, all right, the residual sum of squares divided by the total sum of squares, that gives us the portion of the variation in y covered by A. And then we just subtract that from 1. And that gives us the proportion of y covered by B. That's it. That gives us the overlap. It's a proportion. All right. Now, unlike root mean squared error, it's interpreted the same way for every single model. It's the proportion of the variation in y that is accounted for by our model. In this case, just a bivariate model that includes one independent variable. But as we add in other independent variables when we get to multiple regression, it's going to include those as well. Now, there's another way to calculate this. I'm not going to worry you too much with this, but I'll show it to you. We can directly measure B, and that's called the model sum of squares. All right, so we can directly measure the size of this. All right, it's a little less straightforward. It's just the predicted value of y minus the mean, square that, and sum that all up. That's it. Okay, so don't worry too much about why that's the case. I think it's more straightforward to think of R squared in the other terms. All right, and then R squared is just the model sum of squares divided by the total sum of squares. Okay, so assessing model fit, going back to our example data, the R squared here, I ran it through the program and I got an R squared value of 0.065. So we've accounted for only 6.5% of the variation in percent women in the lower legislative chamber in our 173 sample observations. That's not great. Not great. Okay. Now, there's no set interpretation of R squared. Instead, it's generally better to consider alternative models against one another and see which one has a better R squared. So in that sense, right, we'll come back to this in multiple regression, but think of it this way, right? If we have an R squared here of 0.065 and we add another variable in and our R squared triples, right, then that other variable we've added explains a lot of the variation in y. Okay, so that's a variable that we really should be including. Okay, so that's what we're talking about here. Okay, that's the best way to interpret an R squared. Okay. Now, moving on to nominal independent variables. In our running example, x is a ratio level variable, right? 0 to 1. The 0 means something, the 1 means something. Okay, and it's perfectly continuous. Now, we would use a similar calculation or interpretation for interval and ordinal variables. But what about when we have nominal independent variables, right? So for interval and ordinal level variables, you'd simply say, what's the effect of a 1 unit change? When we have nominal independent variables, we need to start thinking differently. So here's an example of a nominal independent variable from the VDEM data set. Same y, right? We have the percent women in lower legislative chamber. Now we have a dummy variable, that 0, 1 binary variable. All right, so here you have a box plot that shows if our x is 0, there is no gender quota in that country for the lower legislative chamber. And x equals 1 means that there is a gender quota. So you can see here there seems to be some relationship, right? We have a couple outliers here. Cuba has no gender quota, but they have really high representation for women. Rwanda does. They're also very high. We can see here, though, that gender quota, countries with gender quotas tend to have more women. Not shocking. Okay, so we have our dummy variable. Takes the values of 0 and 1. 0 means it lacks the trait. 1 means it has the trait. And these variables are certainly correlated with one another, right? Our correlation coefficient, our Pearson's correlation coefficient, is 0.254, okay? Which is a decent correlation. And in fact, it is statistically significant, okay? So it's a decent correlation. Not amazing, but it's pretty good. We can estimate a regression line. Now, of course, it's kind of stupid to draw a line here. You'd basically be drawing one that looks like this. But the middle of that line would be empty. Okay, but we can still estimate it. We can plug it into our beta equation, our alpha equation, and pop out this. All right, and here's what we end up with. Right, we end up with an intercept of 20.6. That's our alpha. We end up with a beta of 6.09. I put the star there to show you that it is statistically significant. And I included the r squared force, which is actually the exact same as the r squared using the other independent variable we were looking at. Now, the interpretation of a dummy variable regression is stupidly easy. The intercept, as you know, is the predicted value of y when x equals 0. So in our case, countries without gender quotas are expected to have 20.6% women. Okay, that's all it is. And then once you add in the coefficient, so notice if x equals 0, then this term cancels out and y equals 20.6. If x equals 1, then what happens? Well, it just ends up being 20.6 plus 6.09. So countries with a gender quota have roughly 6.09% more women in their lower legislative chamber than those without. So you just plug in 1 for x. Countries with quotas should have 20.6 plus 6.09 equals 26.69% women in lower legislative chambers. Okay? Now, keep in mind here that 0 means a lack of the trait, as it does in all dummy variables. But what about when your nominal variable has lots of values? It's not a dummy variable. It's polycotomous. Examples of this would be things like religion, right? You could have Christian, Buddhist, Jewish, Muslim, atheist, agnostic, so on and so forth. You could also have race, right? Black, white, Asian, Hispanic, etc. You could also have geographic region, north, south, east, west, etc. All right? These are very common variables in social sciences. All right? We often use them ourselves, right? Think about all the variables that we've talked about so far this semester. Who'd you vote for? Clinton, Trump, Stein, Johnson, right? What is your race? White, black, Hispanic. Okay, we've talked about these kinds of variables before. So our ANES data set actually has a lot of variables like this. Now, until now, what we've done is we've said, all right, let's pick one value of those out and create a dummy variable for that one. They're white or they're not white, right? People of color in that last lab assignment. All right, or they voted for Trump, or they voted for somebody else, right? So we've turned them into straightforward dummies. But what if we want to tease out the difference between a Clinton voter, a Trump voter, a Stein voter, and a Johnson voter? Well, you can't have one dummy variable for that, and you certainly can't use this plain nominal variable, right, where 1 is equal to Clinton, 2 is equal to Trump, 3 is equal to Stein, 4 is equal to Johnson, because then what does a 1 unit increase actually mean, right? There's a way we deal with this. And this is a nice way to think about transitioning into multiple regression. All right, so here's an example from the VDEM data set. Okay, so we see here another box plot with our nominal variable. This time we have geographic region. The VDEM data set breaks it up into 10 geographic regions. Eastern Europe and Central Asia, Latin America, Middle East, North Africa, Sub-Saharan Africa, Western Europe, and North America are lumped together, kind of oddly enough. East Asia, Southeast Asia, South Asia, the Pacific, and the Caribbean. Right, and you can see there that like Latin America has the highest on average, or actually the average highest is Western Europe and North America. Right, there we see Rwanda is really an outlier. East Asia, Taiwan is kind of an outlier there. Otherwise, everything else fits pretty well within its region. You can't use this variable as it is, right? This is 1 equals Eastern Europe and Central Asia, 2 equals Latin America, 3 equals Middle East and North Africa, so on and so forth. What does it mean to have a 1 unit increase? Increasing from Eastern Europe to Central Asia to Latin America. Is that the same thing as increasing from Latin America to Middle East and North Africa? Who knows? It doesn't make any sense. So you can't use this in a regression. The order doesn't matter. The values themselves don't matter, except in that they differentiate the regions. It's a nominal variable. So instead, what you would do here is you would actually create 10 different dummy variables, one for each value here. So you'd have a dummy variable that is 1 if it's in Eastern Europe or Central Asia and 0 if it's not. Another dummy variable, 1 equals Latin America, 2 equals not, or 0 equals not. Another one where 1 equals Middle East, North Africa, 0 equals not, so on and so forth for all 10 geographic regions. There's an easy way to do this in SPSS. I'll show it to you. It's literally go to transform, create dummy variables. That's it. Okay. Now you would use multiple regression here, so you'd throw in lots of these things. You'd throw in almost all of your dummy variables. However, you have to leave one excluded, sorry, right? So you'd include all but one of these. So you'd include 9 of these. There's an important reason for that. If all are 0, if you include all 10 of them, and they're all simultaneously equal to 0, what's the reference there, right? There are no countries that don't fit into one of these regions. So if we exclude Eastern Europe and Central Asia as the group, and then we interpret each of these, we say, all right, what's the effect of being in Latin America relative to Eastern Europe and Central Asia? It allows for those comparisons. So maybe you decide to exclude Western Europe and North America because they're the highest, or maybe you exclude the Pacific because they're the lowest. Okay, but either way, you need a reference category. All right, that's going to be important for some of you, I imagine, in your analyses for your multiple regression projects. Okay, so a quick review and preview here of what's to come. To assess model fit, we can use the root mean squared error or R squared. All right, and R squared is just how much of Y's variation is explained by X. With dummy variable regression, our beta acts like a switch. If X equals 0, the switch is off, Y equals the intercept. If beta is on, then Y equals the intercept plus beta. Okay. With polycotomous nominal variables, we create a series of dummies. We must exclude one category as a reference. Next up, we'll talk multiple regression. So enjoy. I hope to see you all soon. I'll be posting some stuff about your multiple regression projects in the coming days. Keep an eye out for that. Your lab assignment this week is going to be related to this. So make sure that you keep an eye out for that as well. All right, I will see you all soon. Best of luck.